All right, good morning, everybody. Thanks a lot, Murray, for having me back in Toronto. It's been a while. It's a good trip for me. I brought my son. He was born in Saudi Arabia. He's a Canadian citizen, so it's his first time here in Toronto. So it's a good trip, and all the better to make the visit coincide with teaching a course on combustion chemistry. Something I'm very passionate about. I love combustion, and then you put chemical engineering in combustion, it's like, kill two birds with one stone. It's a great thing. So today what I'm going to talk to you about is kind of the overview of how could you use combustion chemistry to actually understand something practical. Is this working? Yeah. So that's the goal. But the idea is somewhat to motivate you, see if any of you are actually crazy enough like I am to actually pursue this area of combustion chemistry, then you might like this talk and you might attend the lectures afterwards. So part of it is to entice you so you don't go to Murray's talks and you come to my class afterwards and maybe make you a wacko like I am. All right, so we're going to talk about combustion chemistry of future fuels for future engines. But before we even talk about combustion chemistry and the future of fuels and engines, first we need to see what does the future hold for us. So I like to show this video. It's British Petroleum's view of what the future for energy is. And it's pretty much, there's a consensus about this. Most oil companies, international energy agencies, experts that look at outlook on energy, they pretty much have the same idea. So this is a nice way to kind of kick off the talk and just let you know what is the future of energy and where does combustion play a role in that. So, just to give an overview of the video, it kind of paints a clear picture of what the future for energy use is globally. And it's quite clear that at least until the year 2035, probably closer to 2040, 2045, whether we like it or not, petroleum-based fuels are going to be dominating the market. And the reason for that is renewables will grow. Nuclear seems to be stabilizing, not growing significantly. But the large investment to actually meet future energy demands in places like India and China and parts of the world that are growing rapidly can only be met by those sources of energy that are relatively cheap and that are readily available. And so for me, it's interesting. Two things. One is we saw that renewables will be growing and biofuels will play a role in the future, but they'll be blended with conventional petroleum fuels. And for the most part, combustion is going to be the major source of fuel energy for transportation applications and even for stationary power generation in many parts of the world. So where I work is actually an interesting place. It's King Abdullah University of Science and Technology Clean Combustion Research Center. It was basically founded on this type of a vision. Saudi Arabia being the largest petroleum producer in the world and one of the largest exporters of crude oil, needs to remain their market share and their market compatibility, competitiveness in the future. So this center was established basically to enable clean and efficient utilization of fossil fuels and also substitutes for fossil fuels by combustion-generated means. So where I work it's in a place called Jeddah, Saudi Arabia, and it's only about 5 years old. And basically, when it was started, it was based on this forecast that hydrocarbon fuels will dominate for the next several decades. There'll, however, be a gradual shift to lower grade fuels. That means when you take a barrel of crude oil, typically you want to save the lighter ends of the barrel for petrochemicals, and you want to burn the heavier stuff for energy. So things like heavy fuel oil, pet coke, very heavy fuel oils, these are interesting for energy generation. Most of this energy is going to be used for transportation. This is the issues related to combustion are driving combustion to extreme conditions, and we'll be talking about some of those extreme conditions during this plenary and as well as moving onwards. And then global warming and climate change are playing a role. And based on these directions, or based on this forecast for energy and the environment, there's certain directions that the center focuses on. Fuel formulation and diversity, we'll be talking a little bit about that. Efficiency and emissions, carbon capture processes, using computational models, so chemical kinetic models and computational fluid dynamic models to predict combustion, and also coming up with innovative combustion ideas. So that's just an overview of where I'm working and how it fits in with the overall picture of combustion research moving forward in the future. Now, keep in mind, many industries also work on these areas. So we have, I think, speakers coming from GE, from Pratt. Is there a speaker from Pratt?
Yes,
during the field trip. So they also work in these areas. And keep in mind, when an industry works on this, their goals are more near term. Probably they need results in the 1 to 5 year time range. But university, it's a unique place where we can look really long-term horizons. So we look at problems that are going to be facing combustion maybe 15, 20 years down the road. So we talked about the fuels, okay? So the fuels of the future are going to be very different than they are today. And the reason for that is because the engines of the future are going to be different than they are today. So just to give you an overview, I'm sure many of you know what the conventional types of engines are, but an overview: gasoline engines, spark ignition engine. So basically you have a pre-mixed fuel air mixture injected into the cylinder. Ignition is controlled by the initiation of a spark, and the heat release is timed by the propagation of this flame through the cylinder chamber. So you typically have a high temperature burnt gas region resulting in NOx. The efficiency of this engine is limited by the compression ratio, the maximum compression ratio before NOx is achieved. And NOx is characterized by our octane number index. We'll be talking more about octane number in the course of these lecture series, because octane number is a fuel-dependent, chemistry-dependent phenomenon. Okay, so basically the key is a gasoline engine limited by maximum compression ratio that limits the NOx, and that basically lowers the efficiency of the engine. The diesel engine is a compression ignition engine, non-premixed fuel air mixture. So you have the air charged into the cylinder. That cylinder air is compressed to a high temperature and high pressure, and fuel is injected. And the heat release in the engine is controlled by the injection strategy. So you can have a single injection, maybe multiple injections, and the injection timing basically controls how the heat release ensues afterwards. So you typically have a high temperature diffusion flame that results in NOx. There's lots of rich mixtures leading to soot formation, but typically you could achieve very high compression ratio in these engines because you don't have the issue of engine NOx in a diesel engine. So if you look at a typical engine map, this is showing you temperature versus equivalence ratio, and it's showing you most engines at high temperatures and high equivalence ratios, you have a lot of soot being formed. So this is kind of the region of where a diesel engine operates. At very high temperatures and leaner equivalence ratios, you tend to get more NOx. So typically this is where the gasoline engine operates. You want to avoid both these regions of high soot and high NOx. So the engine manufacturers try to basically skirt the operating conditions, try to get to somewhat lower temperatures, leaner conditions, so you don't really hit that NOx boundary and you stay below the soot boundary. So that's a conventional engine. That's how people are trying to address these issues today. Of course, there's many variants on SI engines and CI engines. What we're looking at in the future is some kind of hybridized type engines. You guys have probably heard of these homogeneous charge compression ignition engine. This is somewhat of a specific type of advanced engine technology. I like to lump them all together in terms of low temperature combustion engines. So HCCI just being one of these different types of low temperature combustion engines. Basically here you have a premixed fuel air mixture, very lean conditions, but then you ignite that mixture not with a spark plug, but by compression. So it's a compression auto-ignition event. You can typically obtain very high compression ratios, getting diesel-like efficiencies. Since you're operating lean, you get leaner conditions. You get no soot or very low soot, and lower temperatures in the cylinder result in less thermal NOx being generated. And then you look at the engine operating map, and you see that these engines try to operate in this region of lower temperatures and leaner conditions, so they don't really hit that NOx and soot region. So the key thing to note that is in all of these advanced engines, the primary factor that's controlling heat release and subsequent combustion is the chemical kinetics of the fuel. So how the fuel is burning and basically the combustion chemistry of the fuel. So these low temperature combustion engines, the hardware features are similar to gasoline and diesel engines with some minor modifications. You can achieve these diesel-like efficiencies, low NOx, low soot. Various acronyms, PCCI is premixed charge compression ignition, homogeneous charge compression ignition, SCCI I think is stratified, right? Stratified charge. They even have spark-assisted compression ignition. Different variants, all the same principles underneath. Basically, the fuel effects are indispensable. Auto-ignition, volatility, density, surface tension, all play a key role in these technologies. So whatever we can do to understand the fuel effect is going to really help in designing these engines for the future. So that's the basic question I have, is what are the effects of fuel's molecular structure on combustion and emissions? And these are interesting questions because different fuels have different molecular structures. If you look at a petroleum fuel, you have lots of branched hydrocarbons, linear hydrocarbons, some aromatics. But if you look at biofuels and synthetic bio-derived fuels, their molecular structures are fairly different. Biodiesel has ester moieties. If you look at a synthetic jet fuel, gas to liquid, there's no aromatics. So how do all these different features then affect the combustion process? And can we predict these just by looking at the types of components that are there in the fuel? These are the questions I'm trying to answer. In order to do this, I try to develop what we call molecular level combustion models. And of course, there's many groups in the world that do this kind of work, Lawrence Livermore National Lab being one. There's a group in Ireland, National University of Ireland in Galway, a couple of groups in France, in Italy as well, and one in China. So there's about, I'd say, 5 to 7 groups in the world that try to do these very high-level molecular combustion models. And the idea is if you have a very good idea, this picture basically tells you if you have a very good idea of how a fuel burns inside of an engine, the chemistry, then you can basically put this chemistry into an engine CFD model and hopefully use it to predict something that's important, like maybe the octane rating, the maximum compression ratio that could be achieved, or the emissions that are coming out. So this is the goal. Okay, we're trying to get from a very fundamental understanding of fuel. Fuel is different types of molecules. What are the chemical features of those fuels? And then we want to try to enable our understanding at a very fundamental level to understand what's happening in an engine. So at a very fundamental level, we try to do experiments in zero-dimensional and one-dimensional combustion systems. And over the course of this lecture, I think the third lecture, we'll talk about what are these different types of experiments that we're interested in. And based on those experiments, we can do modeling in things like Chemkin or Cantera and develop these detailed chemical kinetic models. With those models then, because they're very complex, thousands of species, tens of thousands of reactions, if we go to computational fluid dynamics simulations, we're limited by the number of species that could be basically integrated. Basically, the number of differential equations related to the number of species that can be solved in your reacting flow simulation. So as a result, you need to reduce the number of species. So we have a model reduction, and then we can start simulating things in two-dimensional combustion systems. This is a 2D spray chamber. So instead of a pre-mixed fuel air mixture, now you have a spray penetrating into a chamber, spray vaporization, and then combustion. So that's a more complex phenomena than a fundamental 0D and 1D system. That we can try to simulate with CFD with skeletal kinetic models. And then ultimately, we try to reduce those skeletal models to reduced models, probably another factor of 5 to 10 reduction in chemical species, and then use these in practical engine simulations. So I try to work with, I'm mainly in this area, developing the detailed chemical kinetic models, but I work with people to do the reduction so that the quality of the kinetics models are retained when you go to the CFD. So I'll be showing some results of how we do these CFD simulations. And then I have a colleague in Kaust who does engine simulations, who uses the models and that I further reduce. So we really can go from the very fundamental level to the applied level. So in order to do this fundamental combustion chemistry or chemical kinetics investigations, we need a wide range of experiments. And the reason for this is because an engine is very complex. Here I like to put it like a puzzle. So the engine is pistons moving up and down. As a result, temperature is changing as a function of time. Pressure is changing as a function of time. Mixture fraction changes depending if you're premixed or non-premixed. If you're in a stratified charge, you could have different levels of mixing throughout the cylinder. And the mixing of the fuel and air, also the modes of mixing vary as the cycle proceeds. So because of this wide range of temperatures, pressures, mixing conditions, the engine is not a good place to do a fundamental chemistry experiment. So basically, we need a number of different fundamental experiments that operate at conditions that are relevant to an engine. So we can operate these premixed stirred reactors at temperatures from 500 to 1,000 Kelvin, similar to what you would see in an engine, maybe pressures up to 10 bar, but you can't go to very high pressures. So you would use something like a shock tube to get to very high pressures, maybe up to 50 bar, 60 bar pressures relevant of what's happening in an engine. You could do different types of non-premixed flames, co-flow diffusion flames, counterflow diffusion flames, rapid compression machine experiments, or flow reactor experiments. We'll talk about more of these later in this lecture series, but the main idea here is in order to develop a model that's capable of predicting, say, ignition, flame propagation, emissions in an engine, you really need a lot of different fundamental experiments for which your model needs to be validated against. And with that information, then you could say, OK, my model is going to work well in an engine configuration. So this is a process of how you design these chemical kinetic models. So you first start with generating an elementary reaction set and assign reaction rates. We'll be going through this whole process as this course goes on, okay? But this is just the overview. You generate these reaction sets and assign reaction rates to all the species. You then determine thermochemical and transport parameters for all your species. You conduct these controlled validation experiments, shock tubes, stirred reactors, flames. You simulate those experiments using the detailed chemical kinetics in a reacting flow simulation like in Chemkin or Cantera. And then you compare your experiments with simulations. If you're satisfactory in your agreement, you could stop there. But most of the times, you're unsatisfactory. So you need to do some refinement, either modification of the rates, maybe changing the thermal chemistry. So you typically use things like sensitivity analysis to refine the model and then hopefully get to the satisfactory model in the end. So let's talk about this comprehensive combustion chemistry and why do we need this kind of a comprehensive approach to understanding the chemistry of combustion. Well, this is actually a graph and a figure that my colleague Mark O'Male at Lawrence Livermore came up with. So if you look and say, it's just it's a phenomenological understanding, okay? So just big picture. Say you have a reactor, this is the reactor temperature, and this is the reactivity of the fuel. So you're going from low temperature, say 500 Kelvin, up to 1500 Kelvin. Even the scale is arbitrary, just from low temperature to high temperature, and you're looking at global reactivity in this reactor. It could be an engine, could be a gas turbine, doesn't really matter. So if you see above 900 Kelvin, typically, if you only had high temperature type combustion reactions in your chemical kinetic model, you would find that when you put this fuel air mixture in your reactor, it would only start reacting at high temperatures, say above 900 Kelvin. So you'd see a gradual increase in reactivity and then eventually reaching a steady reactivity. And that's what we call high temperature combustion. Those types of chemistry that happen at temperatures typically above 900 to 1000 Kelvin. However, from practical experience over probably a century now, we know that reactions happen at lower temperatures. And the way these reactions happening are by a series of what we call low temperature degenerate chain branching. And we'll go through all this sequence in the course of this lecture. But basically, if you wanted to simulate what's happening and predict reactivity at lower temperatures, you would find if you include all these types of reactions in your model, you'd see that, OK, now I'm starting to get reactivity of this fuel air mixture at lower temperatures, below 750 Kelvin. And then you'd reach some kind of a stable operating condition. The interesting thing, though, is real fuels don't really operate like this. Because real fuels, what we find is that at low temperatures, if you increase the temperature in the reactor, you get some increase in reactivity. But at some intermediate temperature, typically around 700, 750 Kelvin, the increase in temperature actually causes a decrease in reactivity. And then eventually you cross over to the high temperature region, and then you have an increase in reactivity again. And this NTC, or negative temperature coefficient behavior, is a very complex chemical kinetic phenomenon. And it requires additional chain terminating and chain propagation pathways to be included in your model. So in order for us to say that we're comprehensive in our combustion chemistry modeling, we need to be able to predict all this behavior: low temperature reactivity, intermediate temperature NTC behavior, and high temperature reactivity. And that's what makes our models very complicated and very high level. And in order for you guys to understand the value of this, we'll be going through all these different types of reaction chemistries in the course of this lecture series. OK, so that's an overview of basically 101 of what you could, how would you embark on this adventure of developing a chemical kinetic model. We'll go into much more details later on. Now let's look at, if you had these models, what could you do with it? Because in a plenary, I think that's what you would be interested in. So now you got to fast forward. Imagine you knew how to make all these models, and you knew how to run them, and they were valid. What could you do with these? And that's the remaining of this lecture. We'll talk about what the capabilities of these models are. So as I mentioned before, we have these future engines. And in these future engines, the fuel effects are critical to engine operation. So things like auto-ignition phenomena, flame propagation rates, sooting tendencies, even things like volatility, density, and surface tension. They're physical properties, not chemical kinetic, but they also play a role. And understanding the physical effects also help us to better understand how we develop the chemical kinetic models. So we'll talk about those in more detail as well. So first, let's look at some series of molecules and try to understand, if we had these models, how can we predict these important engine-relevant phenomena. So the first topic will be this combustion chemistry of branched hydrocarbons. Mainly these branched hydrocarbons are important components in diesel and jet fuels. So we're talking about branched alkanes basically means a methyl substitution on a linear alkane backbone. So these hydrotreated renewable fuels and Fischer-Tropsch fuels, they typically have a high concentration of N-alkanes and what we call isoalkanes, or branched hydrocarbons. So we're talking about fuels that basically, if you take an oil or a fat or biomass, for oil or fat, you do deoxygenation, selective catalytic isomerization, and you get a hydrotreated renewable jet or diesel fuel. Biomass, you can do gasification to syngas and then Fischer-Tropsch. With some catalysis, you can also get to these synthetic jet fuels or diesel fuels. And when you look at these fuels, they're different than conventional diesel in that they're only large concentrations of these N-alkanes, so normal alkanes, no oxygenates, no aromatic rings, no double bonds. And these isoalkanes, basically N-alkanes with one or two methyl substitutions. So this is a 2-methyl C15 molecule. This is a 3-methyl C12. This is a dimethyl decane, so a symmetrical 2,9 dimethyl decane. So these are the types of molecules you would see in these synthetic jet fuels and diesel fuels. In order to understand then how these fuels burn, we need to have models for these different types of components. And if you have these models, you can try to understand something that's actually interesting that you see when you run these different types of alkanes in an engine. So I think a fundamental question is, what are the effects of substitution on ignition phenomena? And people have run different types of alkanes in an engine. This is N-heptane. The isomer of N-heptane is 2-methylhexane. It's also C7, except there's a 2-methyl group. 3-methylhexane, so the same C7 molecule, but now you have a branch on the number 3 site rather than number 2, and a 2,4-dimethylpentane. Same thing on the octanes, you have N-octane, a 2-methyl, a 3-methylheptane, and a dimethylhexane. And what they see is if you look at the research octane number, N-heptane has a, by definition, octane number of 0. That's the scale of which a PRF octane number is based. If you add a methyl branch at the number 2 site, you see the octane number increases to 42. That's a significant increase in octane number for just adding from going from a normal alkane to a branched alkane. If you move from 2-methyl to 3-methyl, even interesting, position of the methyl branch causes an increase in the octane number from 42 to 52. And if you add 2 methyl branches, you get an octane number of 83. So as you know, octane number increases, that means reactivity is lower, less tendency for autoignition under a spark ignition engine condition. So the same thing is true for octane. So octane minus 19, 2-methylheptane, 22, 36 for 3-methyl, and a dimethyl gives you 55. So we wanted to understand, can we predict this type of phenomenon? No one had ever predicted it before. And can you predict, based on the molecular structure, how octane number changes? So again, I told you real fuels tend to have larger N-alkanes, would be C15, C16, C17. But to understand these basic effects, we select a smaller surrogate set of molecules to understand what are the effects of branching on ignition properties. So we looked at 4 different types of alkanes, 2-methylheptane, 3-methylheptane, 2,5-dimethylhexane, and N-octane, and try to understand what are the effects of branching on ignition, and also things like flame propagation rates. So actually, I started this kind of work when I moved to Livermore in 2009 after finishing here, and I've been continuing it. So before 2009, Charlie Westbrook at Livermore had a very nice model for N-alkanes from C8 to C16. And so when I got there, this model was already ready. He had the chemistry available for N-alkanes. But there was nothing out there for these branched hydrocarbons. So when I got there, I started developing models for 2-methylalkanes. We did this in 2010. In 2011, 3-methylalkanes. And then in 2012, 2013, since I left Livermore, I've been working on these dimethylalkanes. And again, the main goal was to understand what are these effects on ignition, but then it has other applications as well. People can now use these models for simulating jet fuel surrogates, Fischer-Tropsch fuel surrogates as well. But we won't talk, again, there's many papers that have come out as a result of this, but we'll focus more on just the ignition and flame propagation behavior, because those are engine-relevant phenomena. So again, we built these models, but building a model is not enough if you have no data. We need this fundamental combustion data. So we worked with a lot of experimentalists around the world. Before 2009, there was just some data from a rapid compression machine at NUI Galway. In 2010, I came and worked with Murray, and we did some counterflow flame experiments. And with Philippe Dagot, we did some jet-stirred reactor experiments on some of these molecules. People then started getting more interested in the community. So then in University of Southern California, Fokian's group, Igor Foplis' group started doing flame speed measurements. Seshadri's group at University of California, San Diego started doing counterflow flame ignition and extinction. We got guys to do shock tube at RPI and flow reactor at Princeton. And you start to see that as you start getting the community interested, you get more and more experiments. And then in 2012, 2013, we probably have all of these plus maybe 5 or 6 even additional experiments. So by developing these models, we get experimentalists interested, and they start doing the experiments. Most of the time, they tell us, hey, your model is dumb, and then we go back and fix it. But that's all part of the game. You know, we can only be as smart as the data that's available. And so we develop these models. Experimentalists tell us we're idiots, and then we go back and we fix the models. That's the whole process. But it's still scientific, and it's a valuable effort. So, OK, we had all this data. We have these models. What can you predict? And I'm not going through all the details of, again, how the models and how the experiments were done. We can look at a typical result from the entire study. This is showing you an ignition delay curve. Ignition delay curve basically tells you the ignition delay time as a function of temperature in a premixed fuel-air mixture. So these experiments are done on a shock tube. This is the inverse of temperatures, so low temperatures down here, and then high temperatures. So 1,000 over T of 1 corresponds to 1,000 Kelvin right here. So below 1,000 Kelvin, above 1,000 Kelvin. Ignition delay time on a log scale in terms of seconds. So I told you before, N-octane has an octane number of minus 19. It's the most reactive. You add a methyl branch, octane number goes up. You add a methyl branch at number 3 site, further increase in octane, then dimethylhexane, additional octane benefit, and 2,2-trimethylpentane, which is isooctane, gives you an octane number of 100, which is the other end of your PRF scale. So if you see here the data shown in the symbol and the lines shown in the model, for the most part, okay, qualitatively the ignition delay curves match very well with the experimental data. So at low temperatures, we see this increase in reactivity. At intermediate temperatures, we see a negative temperature coefficient behavior. And at high temperatures, again, an increase in reactivity. There's a slight shift about 50 Kelvin in the experimental data versus the model. We attribute to some of the selections for fuel plus HO2, hydroperoxyl radical chemistry. Later in this lecture series, I'll go into more details on that. But we're aware of what causes these discrepancies, both in the experiments and the model. Now, the key thing to note here is, okay, so if you were going to do an experiment and you wanted to understand these effects of methyl branch on octane number, some people would not know where to do the experiment. They would immediately go to 1200 Kelvin. Interesting thing to note here is above 950 Kelvin, all these fuels have the same reactivity. So if you went and did your shock tube experiment or stirred reactor experiment, and at a high temperature, you would see that all of these fuels have the same reactivity, and they don't really scale with the octane number. So the octane number would suggest a spread in the reactivity. So, however, if you do the experiments and these simulations at lower temperatures, you start to see that this is where the spread exists. And this spread is found in this negative temperature coefficient region. So N-octane is the most reactive, followed by 2-methylheptane, then 3-methylheptane in the red, dimethylhexane, and then isooctane. So we're able to predict now these trends by modeling the ignition chemistry in this NTC region. And this correlates very well with what happens now in an engine. Because this is actually, if you did an engine map and looked at the temperature and pressure, you would find that typical top dead center pressures and temperatures in a knock test are around 830, 835 Kelvin, about 25 to 35 bar, which corresponds well to this region here in ignition delay experiments. So based on this information, we started to say, hey, can we take a shock tube ignition delay time and scale it directly with the research octane number? And this also, people have been trying to do it, but unless they do the experiment at the right conditions or the simulations at the right conditions, they don't get a good correlation. Sorry about the fonts here. I'll have to fix that. So this is ignition delay time on a log scale on the x-axis, and research octane number measured in an engine on the y-axis. So we're trying to relate homogeneous gas phase auto ignition in a shock tube with research octane number in an engine. Two very different experiments, but can we find the right conditions at a shock tube that would correlate well with what you see in an engine? And we did. So around 835 Kelvin, phi of 1, 20 bar, we find that the research octane number can scale very well with this ignition delay measurement or simulation in an engine. And now based on this correlation, we're able to now basically fit this with the regression, with a regression model, and say, can we fill in different types of molecules along this ignition delay curve and match them with research octane number that would be measured in an engine? And I'll show you more of that later. So the key thing to note is these models have now enabled a fundamental experiment and a basic simulation in a shock tube that could be now correlated with something that's very practical that an engine designer would want, like the octane number of a fuel or a mixture of fuels. And then once you have these models, you can start to go into all the details. So a guy who did the engine experiment can't tell you exactly why the methyl branch being on number 2 versus number 3 affects the ignition delay time, or why 2 methyl branches causes a further increase in ignition delay time. But once you have a model, you basically have a map of how the fuel and oxygen react. And once you have this map, you just go and look at the map and you say, hey, I see all the reaction pathways, and I look at the differences in the reaction pathways between one fuel and the other, and you start coming up with the story of how the methyl branch location, methyl branch number affects the ignition chemistry. Again, I'm not going to go into all those details for the sake of time, but we have about 6 or 7 papers about all this. If anyone's interested in more detail, I can answer this question of how methyl branch location affects ignition chemistry and how the number of methyl branches affects ignition chemistry. And we'll be talking about some of that during the course of the lecture, but it requires some additional understanding of all these low temperature chain branching pathways, chain terminating pathways, and so on. Here I highlight in the dimethylhexane molecule, it's actually formation of cyclic ethers. So branching ratios for formation of cyclic ethers in these dimethyl alkanes is actually critical to predicting correctly the ignition delay time, which then scales with the octane number. So it's not a very simple task. You need to really get branching ratios between different types of species formed during low temperature oxidation accurately. What about flame speed? So ignition chemistry for research octane number is a low temperature or intermediate temperature phenomena. But flame speed, premixed laminar flame propagation through a homogeneous fuel-air mixture, is a high temperature phenomena. So these are some measurements done at Foki and Igafopoulos' group by Peter Velou at University of Southern California. So typically these experiments, what they do is they vary the equivalence ratio of the fuel-air mixture and they measure the laminar flame propagation rate. So you see here different isomers of octane again. N-octane has the highest flame speed, shown here in the red. And the model is able to predict this, again, the fastest flame speed for N-octane. There's about a 4 to 5 centimeter per second under prediction in the flame speed. I think this is an experimental error because we have data from Princeton as well because that matches very well with the model. Then we find that 2-methylheptane and 3-methylheptane, shown here in the blue, they have about the same flame speed. So the one methyl branch decreases the flame speed, but the position of the methyl branch doesn't affect the flame speed. But we saw before the position of the methyl branch does affect ignition. And then dimethylhexane, shown here by 2 methyl branches, a further decrease in flame speed. So in terms of flame speed, number of methyl branches causes a decrease in flame speed. One methyl branch, you decrease the flame speed by about 4 to 5 centimeters per second. Another methyl branch, 2 methyl branches, an additional decrease in the flame speed. But the position of these methyl branches doesn't seem to have an effect. Again, if you're able to predict this, you can look into the model and you can rationalize what's happening. And what you would look if you did a reactivity analysis, looking at mole fraction of species that are formed as a function of distance away from the burner port, you would find that these 2-methyl alkanes, 2-methylheptane and 3-methylheptane, the reason they have very similar flame speed is that their intermediate radical pool is about the same. So the methyl radical that's formed, they're about the same order. The C2H3, so vinyl radical is about the same order, and also the H radical. So these important radical intermediates that basically control the flame propagation to the unburnt mixture are similar in these two monomethylated alkanes, and that's why the flame speeds are very similar. I don't plot here N-octane, but what you would find in N-octane is that it has more H radicals and more vinyl radicals and less methyl radicals. And if you have more H radical and more vinyl, you get more branching to high H radicals. You basically get a higher flame propagation rate. If you add a dimethylhexane, again, dimethylhexane is going to give you more methyl and less H radical, and that's why the flame speed would go down. So that's flame speed. Flame speed is important for spark ignition engines. People in the gas turbine industry are interested in ignition and extinction. So when they're flying at 20,000 feet and there's a flame out in the engine, that's an extinction phenomena. So premixed or non-premixed extinction in a gas turbine at altitude. And then fortunately or unfortunately, they can have ignition, a relight phenomena. And again, relight, high altitude relight is a function of the fuel's chemical reactivity. So if you want to do now basic experiments, you could do a non-premixed counterflow flame experiment for ignition, for extinction and ignition as a function of strain rate. These experiments were done by Seshadri's group at San Diego. And basically you see here that the dimethyl alkane, C8H18-25, it has a higher fuel mass fraction required before it extinguishes, meaning it's less reactive. And then these two monomethylated alkanes have the same reactivity. The same thing is true in a counterflow flame ignition. So the dimethylhexane is going to be less reactive versus these monomethylated alkanes. And again, the models can predict this behavior. And it's all related to the same kind of phenomena we saw in a flame speed. The types of intermediate radicals that are formed varies depending on the number of methyl branches. OK, so that was just to tell you for pure component species. We had these different types of alkanes, branched alkanes, linear alkanes. And we saw how combustion chemistry can help us understand some practically relevant phenomena. But now let's go to real fuels. Real fuels are not one component, right? So real fuels are complex mixtures. And that's what we need to do next is if we want to really engage with industry, we need to understand how real fuels are behaving. So now I'll talk about ignition chemistry of gasoline fuels. So petroleum gasoline is a very complex fuel. It's no longer just these N-alkanes and isoalkanes. So we do have these N-alkanes, N-heptane, N-butane. We have these isoalkanes, isopentane, 2-methylhexane, dimethylhexanes. But we also have aromatics, things like toluene and trimethylbenzene. We have cycloalkanes, cyclohexane and cyclopentane. We have alkenes like hexene. So now we have 5 different classes of compounds that we're concerned with. And the fact is that they're across a wide range of carbon numbers. So again, the gasoline fuel is very complex. It's no longer just a few components. It's hundreds of different components in 5, 6 different types of molecular classes. So how are we going to approach this issue of a very complex fuel? So the way the community has evolved to understand complex fuels is by developing surrogates. So many of you have been working on surrogates, so you know this very well. So the most basic surrogate for a gasoline fuel is a primary reference fuel, PRF. That's a mixture of N-heptane and isooctane. That's your octane number surrogate. So if you take 50% heptane, 50% isooctane, you get a PRF 50. It has an octane number of 50. And then you use that to determine the octane number of your real gasoline by doing a CFR engine test. So the most basic gasoline surrogate is a PRF. It's a mixture of heptane and isooctane, which is basically blended to match the octane number of the CFR engine. Some people at Shell, they've come up with other kinds of surrogates, ternary reference fuels. So now you take heptane, isooctane, and toluene, and now you can better match the HC ratio and also better match the aromatic content, which affects the sooting tendency of your gasoline. There are also many types of multi-component surrogates. And this is where I'm primarily interested, is in multi-component surrogates. So in order to develop a multi-component surrogate, you need more information about your fuel. So I like to look at the molecular class distribution. So what we call the paraffin, isoparaffin, olefin, naphthenes, and aromatics, the Peona distribution. Looking at the sensitivity of the fuel. Sensitivity is the RON minus the MON. Again, if we have time in the lecture series, I'll go into more details about sensitivity. But basically, it's more important than actually the individual research octane number or motor octane number. The difference is what really tells you how a fuel will behave under a range of operating conditions. And that's what sensitivity is interesting for. Emissions. So if you want to look at emissions like soot, NOx, you need more components in your surrogate. And things like HCCI engine operation, because it's a chemical kinetic phenomena, you might need more components in your surrogate mixture to accurately predict HCCI engine behavior. So the first thing I like to do when I look at a gasoline is someone comes and gives me a gasoline, I want to know what's in the gasoline. So we started developing some detailed hydrocarbon analysis tools to do this. So we take our gasolines, we put them through DHA analysis to look at what are the different types of compounds that are there. So it's basically a gas chromatograph with a higher resolution mass spectrometer, so you can see all the different types of isomers that are formed. So you dig different peaks, and from there you can quantify the different types of species that are found in your gasoline. Doing a typical DHA gives you things like this: isoparaffins, aromatics, olefins, naphthenes, and normal paraffins, so global class distributions. But I've already told you that a global class distribution is not very useful, because in the case of alkanes, I told you that N-alkanes and isoalkanes, they have very different reactivity. And isoalkanes with different locations of methyl branches have different reactivities. So I need more information than just global distribution. I need also isomer-specific resolution. So to do these tests, we worked with a group in the US, the Coordinated Research Council, to select specific types of gasolines for study. So this is what we call FACE gasoline, Fuels for Advanced Combustion Engine. It's basically a matrix of different types of gasolines with different aromatic content, different normal paraffinic content, different octane numbers, and different sensitivity. So low sensitivity and high sensitivity. We bought all these FACE fuels. We did the compositional analysis, as I'll show you next. And then we tested them in shock tube and rapid compression machines. We developed kinetic models, and then we do kinetic analysis. And in this way, we can better understand how we go about understanding gasoline combustion. So if you look at these different FACE fuels, I'm just going to pick 2 of them for the sake of this talk, FACE A and FACE C. If you look at these 2 FACE fuels, they have a RON of around 84. So 83.5, 84.7, we'll say RON of 84. Interesting thing is the MON is also 84. So that means these are zero sensitivity fuels. RON minus MON is about 0. It's about 1 for phase C, but for the most part, it's considered negligible within the uncertainty of an octane test. The aromatic contents are all very low. The olefinic content is low. These are highly saturated, means they're highly normal paraffin and isoparaffinic fuels. 99% normal paraffins and isoparaffins. And the HC ratios here as well as the average molecular weight. So if an engine guy saw these fuels, what would he do? He'd say, I have a fuel with a RON of 84 and a MON of 84. Hey, I'm just going to take a PRF, heptane isooctane mixture, PRF 84. PRF 84 by definition is a RON of 84. And PRFs by definition also have 0 sensitivity. So it's also a MON of 84. So no aromatics, no olefins. For the most part, if you look at the upper part of this curve, a PRF matches very well what we see here in terms of these real fuels. But if you look at the HC ratio, there's a little bit of a discrepancy. But the average molecular weight is where you start to see a big difference. The PRF, because it's made of heptane and isooctane, 2 very large alkanes, has a much higher molecular weight than your real gasoline fuels. What effects does this really have? We can see later on what this will be. So what I did is, I didn't want to just look at these Piona characterizations. I wanted to look at the full detailed hydrocarbon resolution. And that's what we see here. So we went into these detailed hydrocarbon analyzers, and we started getting actual isomer-specific resolution. And we actually identify 100 to 150 different species in each gasoline. We find that most of the alkanes are actually at the lighter end, butane and pentane. So the PRF takes all the alkanes to be N-heptane. But the real gasoline has things like butane, pentane, some heptane as well. How is that going to affect the reactivity? The branched alkanes are not isooctane. They're mainly C5 to C7 isomers. How is this going to affect now the reactivity of the real fuel? And there's a large number of trimethylpentanes as well. So based on that detailed hydrocarbon analysis, we start to develop a surrogate palette. Not 2 components anymore. We need more components. So the PRF guy would have said heptane, isooctane. These are my 2 components. That's enough. I said, no, my DHA tells me I need more components. I need some lighter alkanes to capture the light end of the distillation curve. So I need some butane in there. I need some lighter isoalkanes. So I chose isopentane, 2-methylhexane as well, and kept isooctane. And we also kept toluene to represent that small fraction of aromatics. And then we develop a chemical kinetic model for a mixture of all these different components. And we try to use that to determine how the real gasoline behaves. How do we develop that surrogate? Well, again, we come back to this figure that I showed before. Ignition delay time as a function of octane number. So the fuels have an octane number of 84. So I take those different components, and I mix them in the right proportions until they give me an ignition delay time that I calculate in Chemkin, which correlates with an octane number of 84 with this correlation that I came up with before. And that's how we develop these surrogates. We build the models. We run them in Chemkin under homogeneous auto-ignition conditions at 20 bar 835 Kelvin. And then we predict what the octane number would be based on this correlation that was developed before. And then we went to the experimentalists and said, hey, can you measure these 3 fuels in your shock tubes and rapid compression machines? Measure for me a phase A fuel, which has a RON of 84 and a MON of 84. Phase C, which has, again, the same RON and the same MON. And a PRF 84. All fuels have the same RON and MON. Will they behave the same in a shock tube and an RCM? And this is what's shown here. So at high temperatures, it's similar to what we saw before. So at very high temperatures, at 20 bar, you start to see that all these fuels have the same reactivity. So a PRF is a very good surrogate for these real gasolines at high temperature combustion conditions. And the model is able to predict that as well. But you start to see the 2 real fuels are the blue is phase C and the red is phase A. At these very low temperature conditions of below 700 Kelvin, you start to see some spread. The PRF in the black is actually more reactive than these real gasoline fuels. So why is that happening? Well, and is that really important? Well, it turns out it may be important because HCCI engines typically try to operate at these very low operating temperatures. And if you go to a rapid compression machine, which operates at even lower temperatures, down to 600, 650 Kelvin, you just start to see the spread even more. So phase C is actually the least reactive in the blue. Phase A is the intermediate reactivity. And the PRF 84 is the most reactive. And we're able to predict all these differences with our models for PRF 84, as well as our models with these multi-component surrogate mixtures. Again, all the details of that there'll be a presentation on that in the symposium. But basically, to distill the story down, is the reason the reactivity changes is because smaller alkanes have less reactivity than larger alkanes. So PRF84 constitutes a lot of heptane, but the real fuels have butane, which actually has less reactivity than N-heptane under low temperature chemistry conditions. And that causes a decrease in the reactivity of the gasolines versus the PRF. Same is true for some of these lighter isoalkanes that we find in the real fuels. Okay, the last part I'll talk about is even more complex. So I started very simple, pure components. I then went to something more complex like gasoline. Most people would have stopped there. But I like to go even more complex. And more complex is something that's even nastier than gasoline or diesel. It's something like a lubricant oil. So I wanted to look at ignition of lubricant oils and try to formulate a way of looking at how does this affect engine behavior. So why do we need to look at the ignition of a lubricant? Most people say, hey, a lubricant, it's not fuel. It never ignites. It's only in lining the cylinders. So it's only there for viscosity and for tribology reasons. It's not there for fuel-related reasons. But interesting thing is some of the new engines, specifically highly boosted direct injection spark ignition engines, have this problem with pre-ignition and super knock. So lubricant oils have been found to have a role in this super knock behavior in an engine. Basically what's happening is when the intake valve opens, you can have lubricant oil droplets basically sheared off either the valve head or the cylinder liner and entrained into the bulk flow. Or you can have, as the piston is moving up and down, some of the lubricant oil droplets can get entrained off the wall and into the bulk flow. And because these lubricants are very high molecular weight hydrocarbons, straight chain alkanes, they're very reactive. And if they get into the bulk fuel air mixture, they can serve as an ignition hotspot and basically lead to a pre-ignition event that then leads to a super knock. So in order, again, to understand do these lubricants really have an effect? And are they really the source of pre-ignition in these engines? First, we need to study what is in the lubricant. So characterizing a lubricant is very challenging. If you've ever seen a lubricant, it's very viscous. It's a very complex mixture. It's not as light as gasoline. You can't just put it in a GC. So you need some very high-resolution tools and new types of data analysis. So I actually have a postdoc who has an expertise in this. He uses FTICR mass spectrometry, so very high-resolution mass spectrometry to look what is actually in a lubricant. And then we start to get these nice pictures of the carbon number distribution in the lubricant. This is a double bond equivalent, tells you the types of paraffins, isoparaffins, aromatics, sulfur hydrocarbons that you find in a real lubricant. Based on this, we can start to say, hey, now I have a better understanding of what's in the lubricant. Can I predict what the combustion would be? What we found is most of these lubricants are very high molecular weight, C20 to C40 N alkanes, and some isoalkanes, and lesser fractions of aromatics. So again, we want to go back and look at what is the effect of these lubricants on ignition in the engine. So again, I showed you here that this piston is moving up and down. This is the cylinder liner. These lubricant oil droplets, they can get entrained into the bulk flow. As they're entrained off the wall into the bulk flow, they can auto-ignite. So basically what we have is we're assuming that this lubricant oil droplet gets into the main cylinder, it mixes with the fuel that's already in the cylinder or the fuel air mixture, and then leads to an ignition phenomenon. Again, a very complex phenomenon. How can we simplify this? So we started doing experiments in an ignition quality tester. What we did is we took an ignition quality tester. It's a constant volume combustion vessel. We started introducing mixtures of fuel with lubricants and then studied the ignition delay time in the ignition quality tester. Again, the goal was just to see, do lubricants really increase the reactivity of the fuel, and what concentrations of lubricants are required to lead to a pre-ignition phenomenon. What we did then is we did real lubricants, but we also selected some surrogates, a C16 N-alkane, a C17 heptadecane, and octadecane, and we mixed these with isooctane and base oils or lubricants and put them into this IQT. This is showing you this is not really the IQT. We don't have images yet of the IQT, but this is a similar experiment called a 2D spray chamber in Sandia, showing you somewhat how this operates. we have one of these vessels as well. So basically, you have spray penetrating into the chamber. As it penetrates into the chamber, it starts vaporizing. So this is without combustion. And then if you look at when it combusts, this is how it will look. So this is a non-reacting spray vaporization, and this is with combustion. So you have soot formation, and you have a longer impingement of the fuel jet to the end wall of this chamber. Similar kind of spray combustion event happens in an IQT. This is just a nicer picture of it in a spray chamber at Sandia with optical access. So these fundamental experiments, again, what I said is we took isooctane, our base fuel, as a surrogate for gasoline, and we mixed different large alkanes with it. And then we took those and we studied them in the IQT. We also took some base oils, different types of base oils, SN100. I won't go into the details of these different types of lubricants. And then we also took a fully formulated SAE 20W50. So the first thing to note here is in the black, it's isooctane. This is, again, inverse temperature versus ignition delay time. The black is isooctane in all these figures. If you first blend in just 1% of lubricant, you start to see that this is where all the ignition delay times fall. So there's about a 10% reduction in the ignition delay time for just a 1% volume fraction addition of these lubricants. So this is quite fascinating. Even 1%, even a small fraction of lubricant entrained into the bulk flow can cause a 10% decrease in ignition delay time. If we now get a 10% addition of lubricant, you can see that the ignition delay time drops to about 75%. Some of the interesting things that we found, though, is that, I don't know if it shows it here. So yeah, it shows it kind of here on this last slide. So the red here is showing the fully formulated SAE 20W50. And the other dots here are showing you the base oils, and then also the hexadecane and heptadecane. The summary is basically that we're able to simulate very well the behavior of fully formulated lubricant with just something like an alkane of C16, C17, or C18. So the fully formulated lubricant, which has lots of different compounds, it also has additives for increased engine wear resistance. All those additives don't seem to be playing a role in the low-speed pre-ignition. And it's mainly the base oils. And the base oils we're able to experimentally characterize quite well with just a simple C16, C17, or C18 and alkane. Now, based on this information, can we predict? Well, we're not quite there yet, but we have a strategy. We have two ways of doing this. One way we're doing it is with Converge. So you guys are doing CFD simulations with Fluent later on in this course. We use another software package called Converge. It's basically to model spray combustion either in a constant volume combustion chamber or in an engine. So we have a mesh of the chamber. Again, this chemistry had to be highly reduced. So we've taken these large alkane models for C16, C17, C18, and really dropped it down in terms of number of species and reactions. And we start doing RANS-based simulations. We're seeing here we're having some discrepancies in the ignition delay time. There's about a 4 or 5 millisecond delay in the experiment versus this simulation. So we're trying to resolve these now. But I'm trying to tell you the strategy here is if we're able to now develop this mesh, put it into a CFD code with reduced chemistry, hopefully we can then predict this type of pre-ignition behavior that we see in the IQT. The other way of doing it is with detailed chemistry. And for that, we have something called a two-stage Lagrangian model. This is a very simple model. You can build it in Chemkin, okay? So it's a simple representation of turbulent jet mixing. So in a spray combustion experiment, you have a fuel spray. It vaporizes and then mixes and reacts. So here we're dumbing it all down. We're forgetting about vaporization. We only have pure gas phase mixing. And then we have turbulent jet mixing based on a two-stage Lagrangian model. Basically, you have two reactors. It's a reactor network. So you have a flame sheet reactor followed by a homogeneous core reactor. They talk to each other, so there's mass and heat transfer between the two. And then you can predict things like ignition delay time and liftoff length. So with these models, we started testing them for heptane. And the advantage here is we can do full chemistry, 10,000 reactions, several thousand species, no problem. And here we've done simulations with heptane. So this is the experiments in the blue and the simulations in the green. And you can see here experiments of spray combustion in a IQT, very complex spray combustion environment. We're able to model it quite well with this simple two-stage Lagrangian model, only about 2 or 3 milliseconds difference in the ignition delay time. So this is promising for us now. So our next goal is to feed our large alkane models into these two-stage Lagrangian codes and see if we can predict that low-speed pre-ignition for things like N-heptadecane, N-octadecane, and an IQT. All right, in summary, I'll wrap it up. So the goal that I've tried to tell you today is that the future of fuels is requiring combustion to become much cleaner. And the result of that is that engines are moving to extreme conditions. In the case of these advanced engines, they're moving to low temperatures, they're moving to highly dilute conditions. And based on that, we need to develop chemical kinetic models for fuels under these extreme conditions. The way we do this is we try to understand first what's there in the fuel, doing these molecular level characterizations. It could be gasoline fuel, diesel fuel, jet fuel, lube oils. It doesn't matter. I think we need to have a good understanding of what's in the fuel. Based on that, we can start to formulate surrogates. And you only formulate the surrogate in the accuracy and the complexity to which the phenomena you want to predict. So in the case of gasoline, I wanted to predict something very complex, like NTC ignition. So I needed more species. But in the lube oil, all I care about is some pre-ignition phenomena. I don't really care about NTC behavior, high temperature, low temperature. I just want pre-ignition as a global phenomena. So I can pick a much simpler surrogate. The goal here is you want to reproduce the real fuel characteristics in terms of HC ratio, functional groups, molecular weight, ignition quality, and whatever other targets that you want. You then develop your chemical kinetic models based on this model fuel formulation. You can then validate your models against fundamental experiments. Using those models and experiments, you then develop insights and simulation tools that help you predict practical, optimal conditions for fuel design in an engine. And then ultimately, I think if we have this approach, we can start developing engines together with the types of fuels that are being blended for future applications. In conclusion, my goal was to tell you today that we can develop these types of validated chemistry models, and they can eventually be used to understand things that are happening in practical applications. I gave a few examples of flame propagation rates, knock ratings in engines, and also pre-ignition in low-speed pre-ignition in engines. I showed you that these chemical kinetic models can be developed for branched hydrocarbons to understand octane, gasoline fuels to understand, again, octane or ignition behavior, and also, hopefully, lubricant oils, which is also a work in progress right now. And finally, I'll just say this plenary was basically to tell you that combustion is a very complex science. It's a fascinating science, but it requires engineers. And I'm an engineer. A chemist would look at a lot of this work and say it's all engineering. So you guys might be scared combustion chemistry is too much chemistry. Trust me, it's not. This is engineering. This is chemical engineering. And what we're trying to do is we're trying to engineer chemistry of fuels so we better understand practical phenomena. And if you're not too afraid of this type of field, then feel free to attend the lectures over the next couple of days. Thanks.